In this lecture, we will be covering rules of differentiation. So the first rule that we will cover will deal with the derivative of a constant function. And in deriving this, we will recall the definition of the derivative of a function and recall that the derivative of a function, so if we're given f of x, its derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. In this case, where our function is identically just equal to a constant c, if we evaluate that function as at x plus h, it's just c. When we then evaluate it at x, it's also c. So the numerator in our difference quotient will be 0. And so that's a very quick proof that if you have a function that's constant, its derivative is identically equal to 0. But this also should make sense. Remember that what a derivative is measuring is an instantaneous rate of change with respect to the independent variable. If a function is constant, like if it's f of x equals 2, it's never changing. Always has the same value. So its rate of change, its instantaneous rate of change, or even an average rate of change, as we saw in our difference quotient, will be 0. So for example, pretty simple here, if you have a function that's just g of x equals 4, its derivative is just a function g prime of x equals 0. But we're going to revisit this a lot throughout our rules. We're going to look at a lot of different rules for differentiation here. Some of them we will derive and prove. Some of them we won't, in the interest of time. But each one of them will be using this definition. So any differentiation rule that we learn really is going to be a shortcut for this definition of derivative. One of the really key rules in differentiation is this idea of power rule. And this is power rule when your exponent is a natural number. So this bold N stands for the natural numbers. That's the counting numbers. So 1, 2, 3, 4, so on and so forth. If your function is just x to the n, then the derivative of that function is nx to the n minus 1. So you want to think of it as, your power rule says, you take that exponent, bring it out front, and then reduce the exponent by 1. So for instance, when we have g of x equals x to the 4th, g prime of x, power rule says take the 4 and bring it out front, and then reduce that exponent by 1. We get 4x cubed. This is a rule that has a cool derivation, and it's a really interesting rule, the technique we use to derive it, but it's also really key. You want to have this rule down cold. Any differentiation question like this with power rule should be second nature. Okay, so how do we actually prove this? Well, we use a factorization. So it is the case that if you take a number b to the n and then subtract a to the n, you can factor out a b minus a, and what's left is b to the n minus 1 plus b to the n minus 2 times a plus b to the n minus 3 times a squared, so on and so forth down to b a to the n minus 2 plus a to the n minus 1. And if you look at the exponents here, if you were to add them, the exponents are always adding to n minus 1. But you can actually just do this out. You can FOIL this out, and then you'll recover b to the n minus a to the n. And this then means if a and b differ, we can divide both sides by this b minus a. So b to the n minus a to the n over b minus a will be equal to what's in the parentheses here on the right-hand side. B to the n minus 1 plus b to the n minus 2 a to the 1 plus b to the n minus 3 a squared down to b a to the n minus 2 plus a to the n minus 1. Now, if we look at the right-hand side of our expression here, if we let b approach a, let's think about what happens. As b approaches a, b to the n minus 1 approaches a to the n minus 1. B to the n minus 2 is approaching a to the n minus 2. But then you have an a to the 1, and if you actually went all the way, took the limit as b goes to a, this would become a to the n minus 2. So you'd have the same base, so they would add. A to the n minus 2 times a to the 1 is a to the n minus 1. And you can make the same argument for each one of these terms. Note what we have here now is n copies of the same term. And think of it this way, the way we count that, this b to the n minus 1 would have a partner term of a to the 0. So you have a to the 0, a to the 1, a to the 2, up to a to the n minus 1. So that's counting that starts at 0 and ends at n minus 1. So we have n of these terms. This means that the limit as b approaches a of our left-hand side, b to the n minus a to the n over b minus a, is the limit of the right-hand side as b approaches a, which we see now is the sum of n copies of the same term. So it's n times a to the n minus 1. Now, with this in mind, let b be equal to x plus h, and let's call a x. If we do that, this expression here, which we'll label as expression star, star becomes the following: the limit as b approaches a, b to the n is x plus h to the n. A was x, so we have x to the n over b minus a. But now let's note, what's b minus a? actually do the subtraction here. B minus A is x plus h minus x. So B minus A is h. B approaching A means h approaches 0. And if B approaches A, then h, which is B minus A, is approaching 0. So the limit as B goes to A can be replaced with the limit as h goes to 0, x plus h to the n minus x to the n over h, which we notice this is the definition of f prime of x when our f of x is x to the n. This is f of x plus h, right? Evaluate x to the n at x plus h, minus f of x over h. But we also noted, so that's the definition of f prime of x, but our star, we can use the right-hand side. So this was the left-hand side of star, and we noted that that's by definition f prime of x. But the right-hand side of star says we can plug in x for a. So this is also equal to nx to the n minus 1. So these two must be the same. So this gives us the formula, well, the derivation of the formula, power rule, which is one of the most important differentiation rules in calculus. And again, you want to have this down cold. So, now that we have our differentiation rule of power rule, the next step is to think about linear combinations. Linear combinations of functions. By definition, we have two functions, f and g. A linear combination is just a new function where you can scale each of the originals by a constant and then add them. And our theorem for the derivative of linear combinations says that the derivative of such a linear combination, so you have a times f of x plus b times g of x. You can split up the derivative into the sum of derivatives and then factor out the constants. Effectively, what this tells you is that you can go through a question like this one and do the derivatives one term at a time. So in this case, f prime of x can be obtained by first differentiating the first term, and that 4 doesn't affect things. It hangs out, but we do our power rule. So 4 times 3, bring the 3 out front, x, reduce the power of x by 1, x squared. Then, to that we add the derivative of the next term. So the 7 stays, and power rule says this is x to the 1 power, so that would be 7 times 1, x to the 0. So this is 12x squared plus 7, as x to the 0 would be 1. Pretty naturally feeling process there. Let's actually prove this and see how this is a result of the definition of derivative. And this one is easier than the previous. So let's take our derivative of our linear combination, a times f of x plus b times g of x. And so remember this notation, this derivative with respect to x of what's in here. By definition, this is the limit as h goes to 0. First, we evaluate this whole expression at x plus h. So we have a times f of x plus h plus b times g of x plus h minus this evaluated at just x. So minus a times f of x plus b times g of x, all over h, which we've already written. Now, we regroup things, rewrite things a bit. So this is the limit as h approaches 0. We're going to group things in terms of these constants. So we first see that we have terms involving a. So let's put those together. So we'll have a times f of x plus h minus a times f of x. And then the other terms have b's, and we'll do those together. So we have plus b times g of x plus h minus b times g of x, all over h. We can now start using some limit laws. This is the limit as h goes to 0. Well, first of all, you can see that you can factor out an a between these two terms. So we'll have a times that difference quotient, f of x plus h minus f of x over h. And we're also going to use our limit law, our sum law, to split this up into the sum of two limits, which we know exist because the derivatives of f and g exist. So we split this into the sum of two limits and at the same time factored out the common b here in the g terms and the common a here in the f terms. So this will be, now we can take those limits outside, rather, we can take the constants outside the limits. So this becomes limit as h goes to 0, a times the limit as h goes to 0 of f of x plus h minus f of x all over h plus b times the limit as h goes to 0 of g of x plus h minus g of x over h. And now we notice this is nothing more than the definition of f prime of x, and this limit expression is nothing more than the definition of g prime of x. Which is what we wanted to show, that the derivative of a linear combination is the linear combination of the derivatives. So that shows us the rule, and again, it's really important to be mindful of this definition of derivative. Because anytime you're doing differentiation rules, it is in fact this definition of derivative that you're using, and remember where that came from. This came from taking the slope, so pre-limit, this quotient, difference quotient gives you the limit of a secant line. When you introduce the limit, rather I should say the slope of a secant line. When you introduce the limit, the whole thing becomes the slope of a tangent line. We also can think of this, remember, this difference quotient as an average rate of change over an interval of length h. When h goes to 0, that becomes an instantaneous rate of change. So when we do these types of rules, this power rule or a power rule in a case of a linear combination, we are using the definition of derivative. Again, it's like the idea of we're driving a car, but we don't necessarily have our hands inside the engine when we're driving it. One repercussion of this is that if we have a polynomial, and this expression is just a general way to write a polynomial, x to the n would be the highest power of x appearing in the expression, b to the n is bn is its coefficient, and then we have all the lower order terms. If you have a polynomial like this, To get its derivative, we have the following expression. Not something that you have to worry about memorizing. Rather, just notice that to get each term, we're just doing power rule on each term of the original polynomial. So bn x to the n, when we differentiate that term, the n comes out front, and then we reduce the power of x by 1. And then each one of these terms is obtained just by one, doing the same procedure through the polynomial terms. So, for example, suppose we were asked, find the equation to the tangent line of this polynomial. The first thing we would do is calculate the derivative. And again, we can use power rule, and from our linear combination theorem, we know we can go and differentiate term by term. So power rule would say the derivative of the first term is 3x squared. The derivative of the second term, 4x. And the derivative of a constant is 0. Now we know from our interpretation of the derivative that this gives us the slope of the tangent line at any x. We are asked to find the equation of a tangent line at the point 1, 2. So that means we know we're dealing with the point x equals 1. So dy dx, and this is the notation we'll often use, when x equals 1, we just plug in x equals 1 to our expression here, and we get 3 times 1 squared plus 4 times 1, or 7. Now we have the slope of a line and a point on the line, so we know our tangent line is given by y minus the y value, 2, is the slope, 7 times x minus the x value of 1. And that gives us an equation of our tangent line at this point. Now let's start to talk a bit about motion. So now we're going to start to use some of our differentiation rules in these rate of change questions. So as an example, suppose we have a car driving on a track at a speed of 100 feet per second when the brakes are applied at time 0. So you want to think of this as the car is driving on a track, and when the driver hits the brakes, you start a stopwatch. So you start the clock when the brakes are applied. The car's position is given by this function, starting at that time. How far does the car travel before it stops? Well, the first thing we want to think about here is rate of change. This is its position. What do we know is true when the car actually stops? We know that instantaneously its velocity will be 0. And remember that our velocity is the rate of change of position. So we can now use our differentiation rules. So power rule, term by term, 100. We have t to the 1. So you bring the 1 out front, and then you reduce the power of t by 1, so we have t to the 0. And then for this term, same kind of thing. We have minus 5, bring the 2 out front, reduce the power of t by 1. So this gives us 100 minus 10t. And again, we noticed that the car will stop when its instantaneous velocity is 0. So we want to find the time when the velocity is 0. We just found our velocity function here. So we have 100 minus 10t equals 0, or 100 is 10t, or t equals 10. So we know it takes exactly 10 seconds for the car to stop. And by the way, we would also, based on this, we would also assume that we're working in the interval 0, 10, because the idea is the car stops and then it doesn't go backwards, which it would do if we kept running the clock according to this function. So we know it takes 10 seconds for it to stop. But the question, we have to always look at the question. How far does the car travel before it stops? We found when it stops. To find how far the car travels, we need to find its position when it stops, which means, where is it at the 10-second mark? X of t tells us where it is. So x of 10 gives us our solution, or 100 times 10 minus 5 times 10 squared, which is 1,000 minus 5 times 100, or 500 feet. So the car travels a total of 500 feet during this braking process. Another very common type of application, vertical motion. So we mentioned this in an earlier lecture, but we'll use it a bit more now. And again, those of you who have taken or are taking a physics course will have seen some of this before. But if we have a particle projected straight up from an initial height of y0 above the Earth's surface, so think sea level, at time 0, with initial velocity v0, then its height is given by the following function. Minus 1/2 gt squared plus v0 t plus y0, where g is the constant of acceleration due to gravity. If you're working in metric, it's approximately 9.8 meters per second squared. And if you're working in our American units, then it's approximately 32 feet per second squared. Now let's do an example with this. And suppose we have a particle fired upwards from the ground with initial velocity 98 meters per second. How high does it get and where does it land? Well, we're told right off the bat here that our initial velocity is 98 meters per second. We also need the initial position, initial height. Well, if we're told that it's fired upwards from the ground, starts on the ground at 0 meters. So now we apply our formula here. So we have y of t is minus 1/2 gt squared plus v0 t plus y0. And we can start plugging in. Now first, we see we're given this initial velocity in meters per second. So we know we're working in metric, which means our constant for gravity acceleration will be 9.8. So we have minus 1/2 9.8 t squared plus v0 was 98 times t plus 0. Now, similar kind of question. How high does it get and when does it land? So think of this on the ground here. This thing is fired upwards into the air. It goes up. Then, before it actually stops and falls back down, it stops instantaneously and has instantaneous velocity being 0. So at that highest point, we have a 0 velocity. So that's what we'll want to find. So in order to do that, we'll need the velocity function, which again is the derivative of your position function, and use your power rule. So we have t squared here, so the 2 comes out front. So we still have that minus 1/2, the 9.8, but then we have 2t to the 1. And then when we do power rule on the 98t term, the derivative will just be 98. And you see here the 1/2 and the 2's cancel. So this becomes negative 9.8t plus 98. Okay, we have the velocity function, but remember the whole point was to figure out how high does it get. And we noted it reaches its maximum height. When it gets just to its maximum height, pauses for an instant and then comes back down. So that means at that instant it has velocity 0. So we need to solve for v of t equals 0. Using our velocity function here, we have negative 9.8 t equals, well, I should be a little more careful, negative 9.8 t plus 98 equals 0, or 98 equals 9.8 t, or t is 98 over 9.8. Or 10. So at 10 seconds, it gets to its highest point. And we're asked, how high does it get? So just like in the car question, we need to find its position at that moment. So y of 10 will be, we're plugging 10 in to our function here. So it's minus 1/2 times 9.8 times 10 squared plus 98 times 10. Or minus 1/2 times 9.8 is minus 4.9. So minus 4.9 times 100 plus 980. That's minus 490 plus 980, or 490 meters. So this gives us its highest point. Now, if we also want to answer the other question, when does it land? Yeah, so this is our highest point. To find the landing, well, it lands when it's actually a height of 0 off the ground. So we want to know what are the roots of y of t. So we take our function here and find its roots. So in order to do that, y of t was this expression here. So we can write this as minus 4.9 t squared plus 98t. And if we set that equal to 0, then we have 98t is 4.9 t squared. This does have one root of t equals 0. And the other root will be given by 98 equals 4.9t, which means t is 98 over 4.9, or 20 seconds. So 20 seconds is when it lands, and its height, maximum height, was 490 meters. We can also have rate of change questions where they're mathematical and not so application based. So suppose we have a rectangle. It has a side x, and then it has a side of 5x, and we're asked to find the rate of change of its area with respect to x. Well, we know area of a rectangle is length times width, so we have 5x squared. And if we want the rate of change of that area with respect to x, we would do our power rule on this 5x squared and get an answer of 10x. So we can have these types of rate of change questions that are also geometric. Now, remember the key lesson to take from this. Our focus was on a few differentiation rules: constant rule, power rule, and then the derivative of a linear combination is the linear combination of the derivatives. But we now see how we can use those in this context of rates of change and tangent lines that we had looked at when we first introduced the concept of derivative. Now we have more complicated differentiation rules to go through, but these are three of the very fundamental ones that you want to have down cold.